Because of its recursive nature, computing the Fibonacci sequence via brute force is computationally expensive. However, the Fibonacci numbers have a simple and beautiful closed-form expression written in terms of the golden ratio and the conjugate golden ratio. In this video, we are going to derive it from first principles, learning two powerful mathematical techniques along the way: generating functions and eigenvalue decompositions. First, let's zoom in on the Fibonacci numbers. The zeroth Fibonacci number f0 is 0, the first Fibonacci number f1 is 1, and by definition, the rest are given by the sum of the two preceding Fibonacci numbers. Because of this, they grow insanely fast. But that's not the problem. Let's take a look at what happens when we compute the Fibonacci numbers recursively. f0 and f1 are given. These are our terminating conditions. To find f2, we compute f1 and f0. To find f3, we compute f2 and f1. To find f4, we compute f3 and f2, and so on. When computing the Fibonacci numbers recursively, the number of function calls also grows insanely fast. How fast? Let's see. f0 and f1 require only one call, as they are terminating conditions. f2 requires 3 calls, f3 requires 5, f4 requires 9, f5 requires 15, and so on. In general, fn requires 2 times fn plus 1 minus 1 function calls. This is a problem in practice. How to solve this? First attempt, finding an explicit formula via generating functions. But what are generating functions? Suppose that we have a sequence an, which we slap onto a power series as coefficients. The resulting expression is called the generating function of an. There are all sorts of potential issues raised by the convergence properties of power series, but we won't deal with them. For our purposes, a generating function is a clothesline on which we hang up a sequence of numbers for display. As Herbert Wilf phrases it in his book Generating Functionology, which is the book on the subject. We are only interested in the combinatorial properties of generating functions. Let's see an example. The generating function of the binomial coefficients. If we take n over k, multiply it by x to the k, and sum over k, we obtain the polynomial 1 plus x to the n. This is given by the famous Newton's binomial theorem. Another example, 1 over n factorial, whose generating function is our good old friend, the exponential function. One more example, the most important one for our purposes, the geometric series. If we take q to the n, multiply it by x to the n, and sum over n, we obtain the rational function 1 over 1 minus q times x. Q is called the quotient of the series. Yes, I know, convergence and whatever, but let's suspend our mathematical precision and go rock and roll with generating functions. The generating function we want to study is the Fibonacci generating function defined by f of x. How can we find an explicit formula for fn with the help of f of x? Simple. If the generating functions for the sequences an and bn are equal, then an and bn must be equal as well. Let's get to it. We start by unwrapping the definition of f of x, writing out the terms one by one. F of x equals f0 plus f1 times x plus f2 times x squared, and so on. Let's focus our attention on the third term, f2 times x squared. We can use the recursion here and write it as f0 plus f1 times x squared. Similarly, we can write the fourth term f3 times x cubed as f2 plus f1 times x cubed. We can do this for all subsequent terms. For simplicity, let's unwrap the parentheses and write f of x in a more suggestive form. Now, the part f0 times x squared plus f1 times x cubed, and so on, can be written as x squared times f0 plus f1 times x, and so on. Similarly, f1 times x squared plus f2 times x cubed, and so on, can be written as x times f1 times x plus f2 times x squared, and so on. Lucky for us, both power series in the parentheses equal f of x, where we use the fact that f0 equals to 0. Thus, we obtain the functional equation f of x equals f0 plus f1x plus x times f of x plus x squared times f of x. We can simplify this even further, as f0 equals 0 and f1 equals 1, we get that f of x equals x plus x times f of x plus x squared times f of x. By arranging all the terms with f of x on one side of the equation, we arrive at f of x minus x times f of x minus x squared times f of x equals x. One last step. Now we can factor out f of x and divide both sides by the polynomial term 1 minus x squared, which gives the closed form expression f of x equals x over 1 minus x squared. We are at the finish line. I'm not going to spell out all the details, but with the magic of partial fraction decomposition, we obtain that f of x is the linear combination of two familiar terms, the generating functions of geometric series. The quotient of the first term is 1 plus square root of 5 over 2, otherwise known as the golden ratio. The quotient of the second term is 1 minus square root of 5 over 2, otherwise known as the conjugate golden ratio. Note that the golden ratio minus the conjugate golden ratio is 1 over the square root of 5. Now, we can interchange the operations with the infinite sum to arrive at our desired formula. Can you recall the most useful property of generating functions? Two generating functions are equal if and only if the underlying sequences are the same. Now you can see where we are going with this. With the help of generating functions, we obtain the well-deserved result, the non-recursive formula for Fibonacci numbers. Even though generating functions are powerful and fun to use, I have to admit we did a bunch of sketchy stuff to get here. I'm a mathematical analyst at heart, and I can't just overlook issues like rearranging the terms of an infinite sum or interchanging it with operations. So, what's the solution? I'll show you another way, this time with linear algebra. Let's talk about the Fibonacci matrix. Let F be a simple 2 by 2 matrix. The first row is 1, 1, while the second row is 1, 0. If we square F, we obtain the matrix 2, 1, and 1, 1. The cube of F is 3, 2, and 2, 1. Let's see a couple more powers. Here's f to the 4, and here's f to the 5. Do you see the general pattern? The nth power of f contains the Fibonacci numbers f, n plus 1, fn, and fn, fn minus 1. Here's a property of F that hints at what we are about to do. F is invariant to matrix transposition, that is, it is symmetric. You guessed right. We are going to apply the spectral theorem for real symmetric matrices, otherwise known as the eigenvalue decomposition theorem. It states that if A is a real and symmetric square matrix, then there exists a P such that A equals P times the diagonal matrix times the inverse of P, where the diagonal matrix contains the eigenvalues of A. This is an extremely powerful theorem, which we are applying to a simple problem. In mathematical terms, we are about to shoot a bird with a cannon. Let's call this diagonal matrix D to simplify the towering computations that we are about to do. Now let's square our matrix A using the eigenvalue decomposition. As matrix multiplication is associative, we can eliminate the p's in the middle, obtaining that A square equals P times D square times the inverse of P. Continuing this process, we get that A to the n equals P times D to the n times the inverse of P. Fortunately for us, computing the nth power of a diagonal matrix is simple. We just have to raise the diagonal elements to the n. Now, recall that the nth power of the Fibonacci matrix is given by the Fibonacci numbers. Using the eigenvalue decomposition of F, we'll eventually arrive at the non-recursive formula for the Fibonacci numbers. Let's get to work. To compute the eigenvalues of F, we have to solve a quadratic equation given by the determinant of F minus x times the identity matrix. This determinant is given by x squared minus x minus 1. By plugging the coefficients into the quadratic solution formula, we see that the roots of x squared minus x minus 1 are given by the golden ratio and the conjugate golden ratio. After crunching some numbers and matrices, we obtain the eigenvalue decomposition of F. By raising it to the nth power, we can already see the formula emerging. After making some room on the screen for the incoming computation, we begin by unwrapping the first matrix product. Now we can easily compute the top left element of the final product. We don't care about the others. By comparing the result of our computation with the nth power of F, we get the desired formula. Here it is once more in its full glory. Even though the non-recursive formula directly computes the nth Fibonacci number, it involves working with floats, which introduces numerical issues. In practice, we are better off computing the powers of F. However, if you think about it for a second, this is quite a remarkable formula. First, it establishes a precise relation between the golden ratio and the Fibonacci numbers. Second, even though the golden ratio and its conjugate are irrational numbers, the result is an integer. In addition, it teaches us a valuable lesson on power series and symmetric matrices. When calculus, algebra, and combinatorics intersect, powerful tools emerge. Thanks for watching, and see you in the next video. Cheers, Tivadar.